We can use our ability to read logarithmic expressions or logarithmic equations, that is, our ability to convert logarithmic equations to exponential ones, in order to solve logarithmic equations such as these. This first question asks about the logarithm of 125 to the base 5. What is this really asking? It's saying, what does the base 5 need to be raised to in order to produce 125? We've seen these written in slightly different forms previously, so let's maybe swap the left sides and the right side. The logarithm of 125 to the base 5 is equal to x. Reading this, I think 5 raised to what exponent gives me 125? Or 5 raised to the power of x gives me 125. And what's the answer? What power does 5 need to be raised to equal 125? One way to do this is to make sure that we have the same base on both sides. So we have a base of 5 raised to our unknown exponent on the left. Now, can we express 125 using base 5? Absolutely. 5 raised to the power of 3 is equal to 125. What we see now is that if the bases are equal, the exponents must be equal as well. For 5 to the power of x to be equal to 5 to the power of 3, I can say, therefore, x must be equal to 3. Let's try this again. So we have the logarithm of 0.01 to the base 10 equal to x. In other words, this is asking 10 raised to what exponent gives me 0.01. So 10 to the power of x is equal to 0.01. We'll do the same thing. On the left-hand side, we have base 10, so we'll try to express the right-hand side to base 10 as well. Notice that 0.01 is really 1 over 100. And 100 can be expressed as 10 to the power of 2, so this is 1 over 10 to the power of 2. Can I write this using the base 10 rather than 1 over 10 to the power of 2? Absolutely. 10 to the power of negative 2 is equal to 1 over 10 to the power of 2. So once again, if 10 to the power of x is supposed to be equal to 10 to the power of negative 2, therefore x must be equal to negative 2. It answers the question, 10 to what power gives me 0.01. To get the hang of this, let's try 2 more. Here we have the logarithm of 1/4 to the base 16 is equal to x. In other words, this question asks 16 raised to what power gives me 1 over 4. So 16 raised to what power to the power of x is equal to 1 over 4. So we'll use the base 16 on the left-hand side, and we'll try to rewrite the right-hand side as 16 raised to an exponent. The way I'm thinking about this is I notice that 16 turns into a 4, and that 4 ends up in the denominator. So that must mean I have a negative exponent. 16 to the power of negative 1 would give me 1 over 16. But how do I turn a 16 into a 4? Well, the square root of 16 is 4. So if I take the square root of 16, in other words, if I take 16 and raise it to the 1/2, I turn it into a 4. So I need to do 2 things to the 16 here. I need to turn it into a 4 and move it to the other side of the fraction line. So I need to raise it to negative 1/2. If 16 to the power of x is supposed to be equal to 16 to the power of negative 1/2, then x must be equal to negative 1/2. And the last one. Here we're asked to take the logarithm of 5 to the power of 7 to the base 5, and we're told that that's equal to x plus 1. Before we start to evaluate 5 to the power of 7, let's see if this sorts itself out. We'll start by trying to convert this logarithmic expression to exponential form the way we did the others. So we have the base 5 raised to the power of x plus 1 gives us 5 to the power of 7. Base 5 raised to the power of x plus 1 gives us 5 to the power of 7. As it turns out, this solves itself. If the bases are equal, the exponents must be equal. If 5 to the power of x plus 1 is supposed to be equal to 5 to the power of 7, then x plus 1 must be equal to 7. Solving for x, we find x is equal to 6. We'll look at a different way to solve the logarithm of 5 to the power of 7 to the base 5. In other words, we'll look at a property of logarithms that allows us to see that the logarithm of 5 to the power of 7 to the base 5 is equal to 7. And this will give us another tool to solve the same problem, but simply converting the logarithmic expression to its exponential form works very well here. But what if our unknown isn't on the other side of the equal sign? So previously, our unknown was the value of x, was the exponent. In this case, it's the value of what we usually term y, the thing we're taking the logarithm of, that's our unknown. This looks a little bit trickier, but let's go back to the same strategy. Let's rewrite this logarithmic equation in exponential form. We'll read it as the base 7 raised to the power of negative 2 gives us x. In other words, the base 7 raised to the power of negative 2 is equal to x. Turns out this one solves itself. All we have to do is evaluate 7 to the power of negative 2. 7 to the power of negative 2 is 1 over 7 squared, or 1 over 49. This next question works the same way. We're told that the logarithm of x plus 1 to the base 8 is equal to 3. Let's rewrite it in exponential form. Gives us 8 raised to the power of 3 is equal to this binomial, x plus 1, the whole expression that we're taking the logarithm of. So 8 to the power of 3 is equal to x plus 1. So to isolate x, we simply subtract 1 from both sides. So we get 8 to the power of 3 minus 1. And we can evaluate 8 to the power of 3. It's 512, and 512 minus 1 is 511. The only version we haven't looked at yet is the one where our base is the unknown. But in fact, these are the problems we're much more familiar with, the ones we looked at before we started talking about logarithms and exponential functions. Let's rewrite it in exponential form. This tells us that x raised to the exponent 4 gives us 625. X raised to the power of 4 gives us 625. How do I undo raising something to the power of 4? I have two options here. I can either take the fourth root of both sides, or I could think of this as raising both sides to the power of a quarter. Taking the fourth root or raising both sides to the power of 1/4 means exactly the same thing. In both cases, we end up with x on the left-hand side, and the fourth root of 625 is 5. That is 5 to the power of 4 is equal to 625. The logarithm of 4 to some base is equal to 2/3. Let's try that in exponential form. So we have the base, x, raised to the power of 2 over 3 gives us 4. X raised to the power of 2 over 3 gives us 4. This is one situation where it's useful for us to think about this second strategy. To eliminate the exponent of 4, we raised the base further to 1 over 4. We can do the same thing here. We can take x to the power of 2 over 3 and raise it to the exponent 3 over 2. If we raise the left-hand side to the power of 3 over 2, we have to, of course, raise the right-hand side to the power of 3 over 2. Our properties of exponents tell us that x to the power of 2/3 further raised to the power of 3 over 2 is equal to x to the power of 2/3 times 3 over 2, which is equal to x to the power of 6 over 6, or x to the power of 1, or just x. So we've isolated x on the left-hand side. 4 to the power of 3 over 2 is the square root of 4 further raised to the power of 3, and the square root of 4 is 2, 2 to the power of 3 is 8.